So what about service maps? If you look at a service map, as an example on the right side, you see that there's a distributed system and all the different, events and calls to the different parts of the map are demonstrated in the in the graph. So distributed tracings reveal connections between services, and a service map displays those connections graphically. This is an example from Elasticsearch's application performance monitoring system. You can see there's a front end making connections to adding a service. Elasticsearch is used to show data about that. You can also have connections to a checkout service, which may in turn have connection to call services, email services, and various other things. Without a service map, it would be hard to visualize and understand some of those connections. So what's a topology? Topology describes how different parts are linked and arranged, different parts of a system in distributed systems. Running on changing our infrastructures can be complicated because of the way these systems connect to each other and dynamically establish and release different connections as they operate. Observability reduces this complexity by creating topology maps, bringing together data from metrics, logs, traces, and user experiences organized in a systematic way. So this is an example from looks like StackFlow. At least StackFlow showed this image source. Okay, so topology-based observability has to do with displaying topologies and understanding topologies in real time. It's a layered map of how everything in the environment connects. It looks somewhat similar to Google Maps, and as at least a metaphor. It shows you where the paths are and the nodes. Shows the big picture, traffic flow, where bottlenecks occur. Give you other data about timing and so on, and relationships in a timescape. So a time travel topology provides unified end-to-end views across the services and applications, making it easier to pinpoint the root cause of any problems, resulting in better customer service. It automates ticket resolutions and reduces problem resolution time, or at least it can help with that. It uses topology-powered observability to filter out noise, drive results, reduces alert noise, helps you focus on what matters, captures expert knowledge in the observability system, and defines pertinent rules and best practices within the system. So in this way, it helps shorten the time for diagnostics and problem solving. This is an example screen from a New Relic tool that gives you time relationships for activities across the topology. There's various use cases, very high pace of innovation. So as changes are made to releases and the capabilities of a topology and the nodes and so on will help you keep up with that. High rate of updates of application software in production. Very diverse set of languages. So you need to be able to look across a distributed system that is composed of multiple components that have different languages. There's a very diverse set of runtimes and operating systems supporting software, databases, dynamic execution environments, rapidly scaling up and down. So it supports full stack observability, tool consolidation, works well with AIOps and DevOps. It supports digital experience and digital transformation monitoring, works well with modern application and architecture monitoring, and supports managed observability services. The relationship change analysis tracks how transaction services, applications, and supporting resources change over time, showing exactly what the relationships were at any point in time and how they shifted before, during, and after each incident. That can track changes in the application's configuration and all the supporting infrastructure in real time, again, before, during, and after each incident. With AI and relationship-based observability, the system knows exactly which components are connected and affect the transactions, preventing false alarms by avoiding confusion between correlation and causation. Okay, there's a little activity here. We recommend you stop the video and spend about 15 minutes on it. Think about how does topology-based observability reduce alert noise? And I made a note here that can help kick off your thinking. You can do a little research on your own as well. But topology-based observability reduces alert noise by showing how all parts of the system, the transaction, services, applications, containers, Kubernetes, infrastructure resources, for example, are connected and how those relationships change over time. By using time travel topology, it tracks configuration changes before, during, and after the alerts. The context allows alerts to be based on real, meaningful changes instead of just isolated signals, which cuts down false positives and alert fatigue. So again, spend about 15 minutes dwelling on that. And assuming you did that, I'm moving on. So let's talk about escalation graphs. What's an escalation graph? It's a temporal graph which consists of nodes and relations. The node of the escalation graph, the nodes represent IT components at specific times. The temporal relations are descriptions of the timelines for each component. Temporal relations always only connect components with their past self each time a significant event occurs in terms of the problem. And dependency relations, the type of relation on an escalation graph that describes how components, broadly speaking, affect each other in terms of various kinds of dependencies. So escalation graphs are a good way to represent the occurrences that lead to an event in a time series manner. So the supporting engineer or SRE can instantaneously be prompted with good insights, leading to speedy resolution of tickets. The graph has two types of relations, the temporal relations and dependency relations, which I defined here. There's something called the 4 T's, which are topology, telemetry, tracing, and time. Remember those 4 T's. They come up on the quiz. So organizations lack an understanding of their environments in real-time topology without visual representations. It helps by merging those 4 T's, the topology, telemetry, tracing, and time, to model the configuration of what's going on with different services, microservices, containers, web services, also monoliths, serverless elements, all running in a cloud or on premises at any point in time. This is an example of it. The 4 T's are represented on a graph. So you got time dimensions and dependency relationships shown on the same graph. You got a customer-facing service, microservices being, supporting some calls, and underneath the database elements, so you can see how it's all working together and all the relationships and the timings. How can you read an escalation graph? It shows a scenario that leads to downtime, starts at 3:55 p.m. on the previous slide. The problem starts with an update to some microservice. Latency spikes are the result of slightly degraded performance characteristics that the microservices have. Because of these increases in latency, the autoscaler decides to add more microservice instances that immediately connect to the database. Unfortunately, the database is not as elastic as the microservice, which causes severe resource contention followed by spikes in timeout errors. And the result is general unavailability of the service for a large number of users. Okay, so that's how difficult timing characteristics can lead to some outages that will need diagnosis. It would be pretty hard to do that without this capability.